apologize, but in Simon, I planned that Simon did the last talk, but if he's sick, so it could be me. And I will talk about mainly hierarchicity in the case of the Wintry model. So if you remember, in daily talk, I wrote here, I didn't wrote the paper, we built some skew product extension over square time surfaces, and this can be applied to more general surface with approximation argument. And I will present what can be done for the Wintry model, which does not belong to that class of skew products. And in the case of the Wintry model, the result is negative, so let me state the theorem. So this is the fraction which is here. And there is an input from Shaika Eskin. And the input from Shaika Eskin is to modify an almost everywhere statements on AB to an all AB. So recall that we have parameter AB for the size of the scatterers. And so for all parameters, for almost every direction, the billiard flow in the Wintry is not very good. This is a negative result, and if you remember that at all, it was a positive result. You get some ergodicity for some skew, but here it's not. So, nevertheless, there is applying the technique that Pat Hooper introduced in this article. If you remember, for each generic theorem, there is a counterpart that can be used to prove that you have some very specific direction for which you do not have the expected generic behavior. And this is the same for ergodicity, actually. And we forgot to mention it in the first talk on Monday. And the theorem is that if for very specific parameters AB, but still for AB rational, and such that so A equal P over Q, B equal P prime over Q prime, and there is a parity condition on P and Q, and the parity condition is actually similar to what they mentioned, is that we need to have some one-cylinder direction. But the reason is a bit different. For AB and Q, what's the condition? We need some even-odd condition. One of them, in each PQ, one of them must be odd and one of them must be even. P odd, Q even, or P even, Q odd. And the same for P prime, just the same for P prime, Q prime. Then, the conclusion is that there exists a big sense of direction for which you do have ergodicity. How's the dimension greater than 1/2? For any theta in lambda, the corresponding billiard flow in direction theta is ergodic. So, yeah, there are a lot of papers, but the techniques, they are basically done here, and here you basically see how you manage to do things. Is the method they use here using essential values. And this is the same kind of argument. You want to produce some essential values. And this also uses essential value, but it is a negative result. So I don't want to put it in the same classification. Because it's hard, building essential values, they build it, but to prove that you are not able to build essential values is something that is much harder, and this is not the argument. You prove that you cannot for another reason, for a reason. And yes, the article of here is quite different, and actually applies in a much more general context, I should say that. Because here we are in a context of a skew product, but what he does here is something which applies for quite general translation surfaces. As soon as you have some parabolic elements which fixes your surface. So you need to have symmetry, but you do not need to have some, to be a skew product over a finite area translation surface. And the techniques of essential values, you can only use it for skew products. But what we saw, but for this one, because it's using other techniques, it's possible. So H uses renormalization with parabolic elements. And applies for surfaces that may not come from a covering. A covering of a compact surface, of compact. And compact, I mean finite number of singularity, compact translation surface. And for all the others, this manifest. So, first, as I think I will present first the argument of right-cyclusive line, and then I will try to survey roughly what is done in the other papers. So, of result. So I will recall the definition of essential values, even if we did that last time. So we fix parameters, so we fix everything. And so imagine that you have a flow or a transformation. So imagine that this is my IET, the IET obtained in MAB. Recall that MAB is my surface Samuel wrote down explicitly the interval exchange. So in MAB for some direction. And recall that the dynamics of this infinite surface is given by a function from x to z2, which tells you, depending on which interval you are, either you stay in the same fundamental domain or you go up or right or left or bottom. So the dynamics in the wing tree is the skew product that I call TF, which goes from x plus z2 to x plus z2, and to point xi maps to txi plus lx. And recall that we have a Kirchhoff-Mazur-Smiley theorem, and we can assume that T is ergodic, and even uniquely ergodic. So, ergodic for the Lebesgue measure, and then X is an interval, T is ergodic for the Lebesgue measure. So what is the essential value for this product? So an essential value is the element of Z2. So I in Z2 is an essential value. If for all A containing X with positive measure, so sorry, mu is my Lebesgue measure. Lebesgue measure on X. So this is a probability measure. There exists N. Such that mu of A, of A, Fn equal I is positive. So what is Fn? Where? Fn is the Birkhoff sum along the point X. So f of x plus f of tx. And as David explained, this corresponds to come back in the base x almost at the same place, and at the same time you shift exactly from the initial copy to the copy I. So I guess to have this definition, yes, this is true. If you are in that set at the beginning, then with positive probability measure, you go to almost the same place and shift it back. And the result of, I guess this is of Klaus-Schmidt, which is ergodicity of the superproduct is equivalent of having all elements of Z2 as an essential value. TF aeronautic equivalent at all elements of Z2 are essential values. So, actually, you do not need the definition of essential values to be able to, for the proof here. The proof here uses an extra proposition about essential values and how we modify them. So, in order to do that, I need to define what is a coboundary for your base dynamics. And so, a coboundary, the definition. So the coboundary, it sounds like a topological thing, but actually it is a topological thing, and you will see that later. But this, I should say, dynamical coboundary. And yeah, there is a somewhat open question that I will present later, whether all dynamical coboundary actually comes from topological coboundary in the context of translation surfaces. A dynamical coboundary is a 40 is a function of the form t minus t.
Which function space are you considering?
Yes, right, I should say that. Let's say continue, but then the topology on X is not the topology of the interval, so I don't want to say that. Let's say L1. Let's say everything is L1 for now. For G in L1. So see if G in L1 for G, and this is L1 of X mu. So, and you have the same definition for continuous coboundary if G may be taken continuous. from continuous coboundary. If G may be continuous. So here I have to warn because the topology you want to consider on your interval is not the standard topology because you have discontinuities for your map. So your map T is not continuous. This definition only works for T continuous. Otherwise it has no sense to ask that this is continuous if G is continuous. So, but there is a topology on the interval that makes T continuous. And what you have to do is sort of duplicate all preimages of singularities. So this is standard procedure which is in Kim. It is possible to build a Cantor set. Cantor set, let's say x prime, with the projection from x prime to x, which is almost one-to-one except on a countable set of points where you have double preimages. And you have the T prime, which goes from x prime to T x prime, which is which is now an homeomorphism, and which commutes with so you have the T prime here, and you have it commutes with T. And this is almost everywhere one-to-one. So anytime you have a measurable property here, you have here. And for topological consideration, you want to consider it here, and you get conclusion here because this is bigger. So anytime you want to do something topological, you have to go to this Cantor stuff. So, why is it called a coboundary? You have this equation, but it does not tell you too much. Oh, there is a problem in the composition. Sorry, G goes from, yeah, you do not know G goes from where to where, so G goes from X to R. So this is a function, F was a function. No, the function F is a coboundary if you can write it that way. Yes. So imagine that F is a coboundary. Then what is f of F? What is the Birkhoff sum of that function? You just apply the definition. So this is G composed with T of x minus G of x plus G of T square of x minus G of Tx plus blah 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 plus G Tn of x minus G Tn minus 1 of x. And as you see, there are cancellations everywhere. And what you get is G Tn of x minus G of x. So which means that your Birkhoff sum actually does not look like a sum, but does look like a function. So which means that for hence, if G was continuous, if G is continuous, then in particular Fn of x is bounded. Which means that, yes, you have your billiard. If you pick such a F for building your product, this means that you remained in a compact set. So there is no chance for ergodicity in that case, in particular. Why is it called a coboundary, and what is the link with topological coboundary? Recall that my function f is built in such way that I pick element in the cohomology, and I say that each time I cross this side, I do some element in my group. Here it was 0, 1. But here I pick a cycle, but there is no reason that I can take a coboundary for building my skew product. And what happens if I take a coboundary? So imagine that here is the surface. Here is my boundary, not a coboundary. But you consider it as a coboundary because each time you cross it, you say that you do plus g each time you cross it. But you have to care about the orientation in which direction you cross it. And what's happened if you look at the vertical flow, which is in that direction, is that if you have a coboundary, so this is a disk because this is a boundary. And my co-boundary is plus G on this boundary, so this is the co-boundary. And what happens if you look at your vertical flow is here when you enter, imagine that my cycle is oriented that way. When you enter here, you do plus G, but after a small amount of time, you do minus G. So what happens is, each time you do something, you just cancel it just after. So any F, so topological co-boundary gives rise to a dynamical co-boundary. And my question is exactly, my open question is exactly about the converse of that state. So, why co-boundary are useful for? So when you have co-boundary, you want to consider cohomology, but that's the statement is somewhat about cohomology. I guess this is also class 3. So this is not function, this is class 3. So you have the same T as before. You have an F, which so let's say that it is L1. And this preserves mu and mu is ergodic. Preserves probability mu ergodic. And T is invertible, it is an IET. And the theorem is if you pick a co-boundary, so for any G in L1 of X mu, if you consider the two skew products TF and T of F plus G, they are actually, there is conjugation between them, are conjugate. So, conjugate, which means that I can build which means that I can find a function here, such that so it's not in F, it's F cross, I go in R, sorry. I want to go in some group, Z2, let's say. And G is also in value in Z2, but it may be any abelian topological locally compact group. So what is the conjugation of the dynamics? Is that you have TF on one side, it's very much as before when you build the contour set. X times G, on the other side you have TF plus G, and you have a function which makes, so it is a Borel homomorphism, a Borel isomorphism here, let's call it phi, such that the diagram commutes, so which exactly tells that TF and TF plus G has exactly the same dynamics.
Sorry, I got confused as to what the assumptions are. You start with F.
You start with F and T and G.
So you're given G.
Yeah, given G, but any G. This is not sorry. Yes, you're right. Is you consider a co-boundary. You add to F some co-boundary. Sorry, I was wrong.
Okay.
You pick G, but you consider the associated co-boundary, and you consider the two dynamics given by F and F plus this co-boundary. And for any such co-boundary, the two dynamics of the skew products are the same. And yes, it's quite simple to express phi in terms of G. It's not a hard deal. And basically, it's the reason why when I say about in the Wintry it's actually a curve. It's not cohomology class. I consider, but this theorem tells us that you can consider it as a cohomology class in any sense.
So in the commutative diagram, the arrow on the far right is also F plus the co-boundary.
Yes, sure. Thank you. Yes. So this is not that useful for essential values, but actually yes, because if you have two transformations which are conjugate, the essential values will be the same. So and essential value. So this is not true. You can manage to find it by yourself. Essential value of F are the same as the essential value of f plus this coboundary. So you can find the proof of that in the book of Klaus Schmidt, and actually his theorem is much more general because there is no assumption of L1 and all that. You should assume only L1, I guess, on the coboundary. But yeah, I do not like too much the book of Klaus Schmidt because the hypothetics are very, very general. You have just a group G, and he does not consider L1 functions, so there are many strain behavior. But on the other side, you have very powerful theorems such as this one. So why is it powerful? Is that because if I have a nice coboundary, I can consider f plus my coboundary and have another transformation. So strategy for this is what Francek and Silurai uses in their proof. So you have f which goes from x to z2, and find so strategy. You start from now, and find G. Find a coboundary that goes from x to what? To alpha z2, where alpha is irrational. Or alpha z times beta z, I do not remember. Let's say u1 plus u2, where, so this is another lattice, where, so this is embedded in R2, and where z2 intersected with zu1 plus zu2 is just reduced to 0. So you have another lattice, but which is completely irrational with respect to the first one. So if you manage to find that, and you apply that, what you get is that the essential values of f is equal to the essential values, the set of essential values of that thing. But oh no, I am not completely right. Yes, so no, you want that f plus that guy takes values in. Sorry. Yes. So, sorry, I erased something. Correct? Sure. That's okay.
It's equivalent.
It's equivalent?
No.
No, because this might be 0. Such that f plus g. So this is somewhat equivalent, but if you want to state it as a general stuff. So such that your sum, so this is also a function that I want to consider as a skew product, takes values in, so I will erase that and write R2 in zu1 plus zu2 with z2 intersected with that guy is reduced to 0. So now I apply the theorem which is here, and the essential values of the two are the same. But this guy takes value in z2. So the set of essential values should be contained in z2 by definition. But this one, all values are taken in something which is completely unrelated to z2, which is z1. So this group here is contained in zu1 plus zu2. So because they have equality, I must belong to the intersection, but the intersection is 0, so my only essential value should be 0. So this is where the magic operates, because this abstract, this almost some abstract stuff, tells you that you do not have any essential value. So now the question is, how do you build a coboundary with that property? And this is because of the renormalization dynamics. There are natural co-boundaries which came from the conservatory cosine. So this is a strategy. And how do we find co-boundaries? Find co-boundaries. And the answer is from the stable answer from the stable space. I will explain what it means, but from the stable space of the conservative Zurich cosine. So recall that the conservative Zurich cycle is something that tells you how your cohomology changes when you make the parallel transfer along the geodesic Teichmuller flow. So recall that you pick a transversal and you look at return, and AT is exactly the transport from your initial point to another point. And recall that function that I consider belongs to H1. So I consider this as an operator on functions on my surface. And what is a stable space? I recall that you have Lyapunov exponents. The stable space is the space which concerns the negative Lyapunov exponents. So let's call it Vs. This is a set of F that belong to my cohomology. Such that what do I need? I need summability. So it's not enough that it goes to 0, because yes, you want to. Yes, this is not enough. Such that the lim. I don't want to use Osseld's theorem here. I want a Vs defined for every translation surface. So sorry, Hess is a translation surface here. But any. Not one which is Osseld's generic. Lim sup as T goes to infinity. So it must be, yes, well, it's a mess, sorry. Log, you want that it is exponential, it decreases exponentially fast. Over T is negative. So actually, this condition is not, you can build a Vs which is much bigger than this one by transforming that into a summability condition on ATF. This might be replaced by a summability condition, a bit similar to what Rodrigo did in his talk, by a summability condition. So basically, you want that the integral of ATF is finite. Of the law. No, of ATF. If you have that, it is an exponential sum. And if you add summability, for sure it's less strong. And so what do I claim is that all functions that belongs to my space Vs are actually co-boundaries. So there is a proposition first. So pick, as before, very abstract, X continuous, so omeo. Let's say that it preserves mu, but it's in topological dynamics. And you pick F in X with value in Z or R on any local group. Z, R, any locally compact abelian group. And if there exists a constancy such that the Delecroix sums are rebounded for any n and any x, then F is a coboundary. If you remember, if you have a coboundary, if you look at iterates, it looks like only one function. So one direction is clear. If you have a coboundary, then this is true. and actually the converse also holds. So this is nice because to prove that something is a continuous coboundary, a measurable coboundary, this is no more true. You have something which is in L1, uniformly in L1 or something like that. And it's much more harder, but finding topological coboundary, you just have to prove that the Birkhoff sums are bounded. And this is the case here. If you remember that general theorem I stated about the application of a Euclid's theorem to deviation of Birkhoff sums, you get exactly that.
Vincent, what if, are you assuming anything about T?
Here, no. Only Omeo.
What if you have periodic points?
Then what?
Then, oh, for all x, sorry, never mind.
Yeah, for all it's true.
Okay.
But I might be wrong, I don't know.
If T is the identity, that's not true, but it's okay.
You want minimality, but you prefer how to have minimality?
It's okay, don't worry about it.
It's okay.
It has to be zero.
Yeah, if you have minimality, you can assume that for one point.
Function can only be zero. If T is identity, the function can only be zero.
So, no, this is, how is it called? Headphone, actually, but there is something else in this story. Go check it on this.
Yes.
And so what? Yes, and so this is a corollary actually of what I did before. So what you need? So what I did before, you need two assumptions. You need some Birkhoff genericity plus Lelièvre genericity. By the very same method, you can prove that any element that belongs to F, and for which the surface actually is recurrent in the compact part, then this is a boundary. So I state a precise lemma. S translation surface such that the GT, so compact, sorry, such that GTS accumulates in the compact part or comes back infinitely often in the compact part of the stratum. Corresponding stratum. Then any F in what I defined there, at the stable space of the surface S, is a topological coboundary. So we have a lot of coboundary, but not a lot. This is only, so in good cases, this is only half the dimension of the space. So you have still G coboundary that you are allowed to play with. And with that, you want to modify a bit your function f by summing a coboundary in order that it takes value in something which is completely rational.
Sorry,
So this is the game.
I'm slightly confused about what the statement is. So a coboundary has to have an associated dynamical.
So the dynamical coboundary here. But it's dynamical topological in that sense. It's continuous. Yes, what is the question?
So this is supposed to be a function on a space on which a group acts, like on which you have a transformation. So I don't see this cohomology class. How is it?
Yes, sorry.
What's the space X and what's the transformation T and how do you get the function
yes,
F?
you're right. You have your translation surface S, and you have a flow on it, which is the translation flow in the vertical direction. And then you pick any segment and you consider the first return back on it. So T from X to X, i.e. T obtained from first return time, from as Poincaré section. And then what you do, you have your section, and you look at the first return time to your interval. So you have rectangles which correspond. So this is identified somewhere to my interval, and this gives me a decomposition of my surface. And what you do is you start with the point which is on the bottom of your interval, and you look at the curve which goes. So it's identified somewhere, and you look at that curve. This is a closed curve in homology, and you just sum up the value you obtain along that curve for your cohomology. So this is, yes, let's call this A. So let's call A, B, C, D. So it seems that all interval exchanges are 4 intervals. And so for each of the intervals, you get a curve in homology, right? And the function I'm considering is not on this interval, on X, consider, I call it F again, but it's not a good idea because F is an element of ds of S, or on homology. And what I consider on the interval is just the intersection of zeta A with my function, my cohomology class. So on X, consider F zeta A on the interval that corresponds to A and etc. Yes, cohomology classes are a special kind of functions.
Well, they produce functions.
They produce functions, yes. Is it more clear? Cool. So now I have a lot of topological collateral to play with. And because Boltzmann theorem is completely measurable, you should expect that your co-boundaries are completely irrational and will destroy all your initial function if it takes value in C2. But, yes, it does not work. And for make the argument of fractal multiply work, you need something very special to be able to apply the strategy. Thus, FU strategy. F should belong to rank 2, so dimension 2, rank 2 SL2R invariance, sub-bundle of the consecutive cosine. So this is useful to have a splitting of the Hodge bundle, as it was presented by Felipe, especially when you have rank 2 sub-bundles, because you can apply that. So we need rank 2 and positive Lyapunov exponent inside, and inside non-zero. So when you have a rank 2 sub-bundle, you have one positive and one negative Lyapunov exponent. And so asking that one of them is non-zero is the same as asking that both of them are non-zero. Non-zero Lyapunov exponents. And this is again, so what does it mean? It means that in your H1, you find something which is rank 2, let's call it E, plus something else. This is dimension 2. And your matrix is diagonal with respect to those two blocks. And all your matrices AT looks like E, 0, 0. So you have two subspaces which are preserved by all your matrices. And this happens in two different cases. Back to our knowledge. The first one is when you do have some arithmetic property related to the field of definition, and the other one, which is one which are interested in right now, is because you have some symmetries. And recall that the surface for the wind tree, the surface we are looking at, looks like that. And we do have symmetries, translation symmetries. And translation symmetries are preserved by the consecutive square cycle. And so we do have many spaces, and so for MAB, H1 of MAB, it splits into many invariant subbundles that I call E plus plus, E plus minus, E minus plus, and E minus minus. And recall that the function we are considering to look at the wind tree model has an horizontal component which belongs to there, and a vertical component which belongs to, so I will use another color. Vertical component. And by chance, those two blocks are 2 by 2. This is dimension 2. So this is just to explain that this works for the wind tree. And so why is that good to have rank 2 and minus a bundle and the function that belongs to that, f should belong to rank 2 and yeah, okay. And so why it works now? So first of all, there is a small trick that I love. So imagine that you are in this situation. So imagine that f belongs to E with dimension E equal to with ESL2R invariant. Sorry, I went very small. So trick, this is very useful. If AT of G goes to 0, then G does not belong to the integer. And the proof is stupid. AT is an integer matrix. So this is a symplectic matrix with an integer coefficient, which is invertible. Oh, sorry. Assume that it is not 0. If it is 0, for sure it goes to 0. S t goes to infinity. AT is an integer matrix, invertible. So, which means that if you pick an integer vector, if you pick an integer vector, the image should be an integer, so it should be 0 or something strictly bigger than 0, but uniformly. And so why is it nice? Because when you look at the stable space of the conservative theoretical cycle restricted to E, so E, if you have oscillated genericity for your surface S, E splits into EU plus ES. So last time I write it as a sorry. You have this stable space ES if the S is oscillated generic. Or actually you only need this lim sup condition. And this ES is dimension 1. And this, recall that this is dimension 2, so you can consider that this is like R2. And so this is dimension 1, and it does not intersect the Z2 lattice. What intersects yes? And that's how you pick your boundary. So you have your F. So F belongs to E, but which coefficient in Z? This is a special kind of vector which is here. And you are able to find a coboundary for almost every direction. You can find a coboundary in there. And you can prove that this takes value in something which is completely irrational. And that way you get only 0 as an eigenvalue. So F in Z, but for most G in, so G is my coboundary, it's no more G composed with T minus G. E S, or with coefficient in R, F plus G takes values. I think this is even for all. In irrational values. So this is a lemma which is in Freizeitkultur by Article. So it takes value in a irrational lattice. So this is not hard. You have to prove it. You have to play with that. This is not that hard. And so that way, if you have, yeah, I write everything. That way you prove that generically you do not have ergodicity. So this is basically the yeah.
Did you want G plus G there, or do you want a cosine?
That
The
co-boundary.
co-boundary.
Yes, but here I pick something which is in a stable space. So this is a
So
co-boundary.
G's already co-boundary.
Yes.
That's,
This is how yes, this is the co-boundary. And so this is very interesting as a proof because it proves that whenever you have this stable space for the in the direction for which you have this oscillated, you have this exponential contraction in some direction, then you are able to apply this lemma and get non-ergodicity. So every direction you may expect some ergodicity, are directions for which oscillateds fail a lot, which means that you do have zero exponents in that direction. This is a consequence of that. So for the wind tree, well, for any rank 2 subbundle, blah blah blah, for the wind tree, the only directions theta for which we may have ergodicity corresponds to yeah, we would say to 0 the Lyapunov exponent. But it's more precise than that. Is about some summability of the co-cycle along some vector space. So what do I mean by 0 Lyapunov exponent is if there exists a vector v such that lim sup as t goes to infinity of log of at v over t is negative, then this implies non-ergodicity. But what basically I sketch here. So if you want to find, if you want to have a candidate for ergodicity, this should go to 0. This should be more or yes, greater or equal to 0. And so this corresponds to the Lyapunov exponent. Because if you have something which is positive, that grows positively, you have a negative Lyapunov exponent as well. So this corresponds to some phenomenon. So a good question here is there a nice characterization of ergodic directions in terms of some integrability of the conservative cycle. Characterization in the wind tree of ergodic directions in terms of 8. And what I expect is something like ergodicity. Yes, ergodicity. Somewhat equivalent to the integrability of ATV. This is integrability? No, AT bounded. So what do you mean? Yes, AT. Very, yes, some boundedness of it. Bounded. Or actually, yeah, bounded. So this is the big question. And just a word about the direction Pat-Hooper constructs with this construction here. They correspond to such behavior because what you get is our zero Lyapunov exponent. So how do you, I have time to explain that? Yes. I have time? I said yes.
2 minutes.
Okay, correct. So pick A equal B equal 1/2. And recall what is nice for proving ergodicity, as we saw in the talk of AB, is the presence of cylinders. And recall that for recurrence we use these cylinders as well. And we use this cylinder. So, and if you look at the direction 45 degrees, this is completely periodic in the wind tree with parameters 1/2 and 1/2. So, which means, wind tree completely periodic, so T AB completely periodic. which means that there exists a parabolic, and all cylinders have the same length. So this means that you have a parabolic stabilizers in that direction. Stabilizer in that direction. And I mean the matrix of the form AA001, where A is non-zero and where this is vertical, this 45 degrees. And in the same way, you can find, you can prove that this direction is minus, what is this angle? I don't know, we can manage to find what is this angle. And in that direction, you also have complete periodicity, and you have another parabolic direction. And this is exactly the setting in which Tatiana was applied. You need to have two transverse directions, for which you have decomposition in completely periodic. You have the surface decomposes in completely periodic stuff, like in the third-one construction in finite case. And there is a condition on the intersection graph of the cylinders you have, but here everything is nice. And what you get, the result of that, so H. So you have two parabolic elements here. So let's go M1 and M2. And what you look in all limit, so in all directions that belong to the limit set of M1 and M2 and that does not correspond to directions of cylinder, you do have ergodicity. Direction in the limit set of M1 and 2. So this is a group generated by two parabolic elements. In the limit set here corresponds to either completely periodic directions or ergodic directions. Okay. Yeah, that will be right.
So you have squares, yeah? What about other fun shapes you can...
Oh, what do you want to know about fun shapes? I have one theorem about fun shapes.
Okay.
Okay, that was the question. So, what fun shapes? So depends on your feeling. So there is one theorem and one conjecture. No, one theorem and two conjectures. So my fun shapes are the ones for which everything has a nice right angles. So you can find it in that nature everywhere. You see. And moreover, there is a special symmetry. But symmetry are in nature, you know. So it's natural. So pick something like that as an obstacle and you put it all over the plane. So what is the theorem? Yeah, so if all the dimensions here are generic, you get some diffusion. And so you make a periodic construction, so you get some periodic billiard. And as the number of angles goes to infinity, the diffusion, so this is a generic diffusion rate. Goes to 0, and moreover there is a speed which is 1 over the number of square root of the number of angles. So, and if you remember that the question I asked you about the limit of Lyapunov exponent in the H plus part, and so this is one case where I was able to, with the help of Anton Dorich, to make the computation. And this is a special case where you are able to compute explicitly the Lyapunov exponent with an explicit formula. The formula is nice actually. It's something like n plus 1 double factorial over n double, n plus n over n plus 1 double factorial. And double factorial meaning that you go 2 by 2 instead of 1 by 1. And so this is one theorem. And there is one full conjecture, which I love, that what happens if you pick regular polygons as obstacles. And this is challenged because in the paper of Concevic, the first Concevic paper in 97 or around, yeah, I think one of the first, he claimed that you have a global asymptotic behavior for obstacle. And in that case, it corresponds to belonging to some abelian strata. And what we should expect is that the diffusion rate goes to 1/2. So, yes, and this is the conjecture, and it's 1/2 of Concevic conjecture. So Concevic, yes. Imagine that we have a global asymptotic for the Akonov exponent, and his conjecture should apply something like that. Yes, that's all for fun obstacles that I know.
Perhaps given the hour, other questions can be informal outside. So let's thank the speaker again.